All right, hello everybody. Today we are going to continue on with our stress analysis. As a reminder so far, what we have covered is we've covered stress due to an axial load, and we said we had an axial stress that was just equal to P over A, and of course that's just right along the axis. We've also covered our torsional stress, and we said that we have our tau is equal to the TC over J. So our third type of stress that we're going to talk about today, draw this little torque, is what happens if we have a beam that is under some kind of bending load. Kind of like that load that I have shown right there on that simply supported beam with the uniform load across the top. And if I were to apply a load like that, you can already, hopefully you can imagine what the shape of the beam would end up looking like, because it would basically sag in the middle and come up on the two sides, right? So if I have this deformed shape and I were to look at the strain of a cross section of this shape, let's get my color here. Remember, that strain is just our change in length over the initial length. If we were to look at a cross section through here and analyze the strain of our beam, what we would see is that we have the top half, in order for it to be in that type of shape, the top half would be compressing or getting shorter, and the bottom half would actually be getting stretched or getting longer. And in between the two, what we end up with is this linear shape. And hopefully you can kind of see how that would work just based on our beam and our beam loading. So if we look at the strain profile, what we see is up on the top where we have the maximum compressive strain, and at the bottom we have this maximum tensile strain and decreasing linearly in between. Right in the middle here where it crosses would be a place where there's zero strain. And if there's zero strain, we're going to call this something special. We're going to call this the neutral axis. And like I said, there is no strain at the neutral axis. We're also going to make this in essence, our y equals 0, or basically our height. We're going to base everything off, so we have a positive direction going up and a negative direction going down. And similar to when we talked about torsion and our distance away from where there's zero stress to the outside fiber, we're going to have the same thing here. And we called that a distance C. So we have the same distance here. We have a positive C going up, or we could say that we have a negative C, the distance from the neutral axis down to the outside fiber in the negative direction. What else can I tell you? This is all based on the fact that we have a positive moment being applied to our beam. If I had a negative moment, you can see how everything would flip, and the top would then be in tension, and the bottom would be in compression, and everything would flip. So with that in mind, we said there's a relationship between stress and strain, and it's linear related, because we said that our stress is equal to our modulus elasticity times our strain from Hooke's law. Because of that, then we know that our stress has to also look exactly like our strain graph. So with that in mind, I would have the exact same shape. The only difference here is I'm going to put a sigma in here for stress, and I'm going to have a maximum in compression on the top and tension on the bottom, and in between it's going to linearly change, going right through that neutral axis where there is zero stress, just like there was zero strain before. So let me draw on a couple little arrows showing that it linearly changes. And once again, this is with this positive moment applied to this beam. And then I'm not going to go through the actual derivation, but you could almost think of this whole thing as summing the moment about some kind of point must be equal to 0. And you can see we have the moment. Surface is acting up. I can see my moment over on this left hand side. I'm counteracting that moment with, in essence, the area of these stresses. And you could probably figure out how I would derive this. I would look at the area, and we know that I have the force would be the area times the stress, and you could go about coming up with the sum of the moments in the other direction. And you can see the posted notes on Blackboard for that derivation. But for what we would end up with is our sigma as a function of y, or our maximum. Let's just start with the maximum stress, since that's what we care about most, is equal to minus mc over I. And with that equation, what we have is this m is our internal moment. That's why it's so important to know your shear and bending moment diagrams, because we need to look at where our moment is maximum along the beam and things like that. Our c is this distance from, let's say the maximum distance, because really it's the maximum distance from what we're calling the neutral axis, which is the centroid of our cross section. So with that c distance being the centroid, and I, hopefully you know, is our moment of inertia for this cross section. The only other thing we need to add in here is our signs. If I do have a negative sign, then that means that our section, or that part of the stress, is negative. It designates compression. And if we have a positive, then we would be in tension. So I can also have a more general term for this equation, and it would say that our stress as a function of y is equal to minus my over I. So basically just replacing the c with a y. Same thing we did with torsion. With torsion, we had a c value and we had a rho. So rho is our generic distance away, and our maximum would be c. Same idea here. Y is the distance up or down, and you're keeping that sign in there. If it's down, it would be a negative direction. And if you have an unsymmetric section, like a T section, I'm going to do an example just a bit with a T section, then the C still will be the distance from the neutral axis. And when we talk about neutral axis or the centroid, you're going to have two different numbers here, right? So you might have a greater distance from the neutral axis to get to the top of the beam than the bottom of the beam. So you'll have two different stresses. And our moment of inertia, our I value for our section, must be about this neutral axis. So with respect to the neutral axis. So if that's true, then I need my neutral axis is very important, and probably the first step you're going to do with these problems if it's a non-symmetric section. So I can find the neutral axis as a review. We said our height, our y for the neutral axis, is equal to the sum of our area times y bar over the sum of our areas. So don't forget that basic equation to find your neutral axis. That should be review. Alright, so with that in mind, I'm going to stop this video here and have a part 2, which will be an actual example. So look for that, and thanks for watching.